Hey guys, this is the video for 2.5 implicit differentiation. So we'll look at implicit versus explicit functions, what implicit differentiation is, the implicit power rule, and related rates. Okay, so implicit versus explicit functions. So we normally write a function with the output variable, normally y, isolated, right? So something like y equals x cubed, or maybe f of x equals x cubed, something like that. And those functions are, we normally just call them functions, but what they are more specifically is they're explicit functions, right? It gives y explicitly as a function of x, right? Y all by itself equals stuff with an x in it. Something like this, where you have y cubed plus x squared, y to the fifth minus x to the fourth equals 11, is still a function. It still inputs an x and outputs a y, but you would sort of have to solve for that y, right? It's maybe difficult to isolate that output variable and make it look like just y equals stuff with an x. And those types of equations are called implicit, right? It gives an implicit relationship between x and y as opposed to an explicit. It's an implicit equation there. And we can still find y prime here. We can still find the derivative of that function y with respect to x. But to do it, we have to use implicit differentiation. So that's what we'll be learning how to do. So to take a derivative implicitly, you're going to look at your equation and you're going to, if we want to find, for example, the derivative with respect to x, we'll differentiate both sides with respect to x, or whatever variable you might be differentiating with respect to. You'll use all the same rules that we've used before whenever you need to, just like we have been. But whenever you see a y, you treat it as just a variable. And so when you take the derivative of it, you sort of have to think of, I need the chain rule, and I'm going to end up multiplying by the derivative of the y, which is y prime. Right? So anytime you take the derivative of something that involves a y being differentiated, then you'll have to multiply by y prime with that chain rule thing. And that's sort of the basis of the implicit differentiation. Once you get that, you'll have a big equation with some x's, y's, and y primes. And to find that derivative, you just solve for that y prime. Okay, so what is the implicit power rule? So it says if y is an implicit function of x, so whenever you're taking the derivative of something like y to the n with respect to x, when you're doing this implicit differentiation, then what's going to pop out is, just like before, you do n times the base of that variable, and then you decrease that exponent by 1, but then you'll multiply by a y prime. Right? So if you take the derivative of something like y to the n, it's n times y to the n minus 1. That should be just like we've been doing before, and then times that y prime, because we took the derivative of a y. All right, so let's do an example here. So this says find y prime given this equation. So you would notice, okay, that's an implicit equation. It doesn't have a y on one side. So to find y prime, we'll have to take the derivative implicitly. So we'll take the derivative of the left and right sides. Since we're finding y prime, then we want to find the derivative with respect to x. Right? So y squared, let's take that derivative. You're going to get 2y, and then to the 2 minus 1, so to the 1. I won't write that. And since that's the derivative of a y, we're going to multiply by y prime. All right, then we have minus 3x cubed, so we just take the derivative like normal. We get 9x squared. There was no y there, so that's all that we get. And then on the other side, we're taking the derivative of a 2, which is 0. All right, so that was the step of differentiating implicitly. And now we want to find y prime. So solving for y prime, we'll add 9x squared over, and then divide by 2y. And there's y prime. Right? Notice it's in terms of x's and y's. And so there is y prime. We found it using implicit differentiation. All right, here we're again given an implicit function, an implicit equation. There's x's and y's all jumbled together. This is find dy dx, right? So dy dx is just the derivative of y with respect to x. It's like y prime. But to get us used to writing it in a different way, we won't use y prime in this example. Instead, we'll just use dy dx. Okay, so we've got x times y squared. So how do we take the derivative of that? We have to treat x as a variable and y as a function of x. And so that means we have to use a product rule where the first guy is just an x and the second guy is a y squared. So when we take the derivative with respect to x of that, we get the first times the derivative of the second would be 2y times y prime, because we took the derivative of something with a y. So first times derivative of the second plus the second, which is y squared, times the derivative of the first. The derivative of x is just 1. So that's the derivative of that first term using the product rule. All right, for the second term, we'll also need to use the product rule. And here, our first term is going to be 2x cubed, and our second term is going to be y cubed. So we're going to add the first, 2x cubed, times the derivative of the second would be 3y squared. And since that's a y that we took the derivative of, we're going to multiply by y prime. And then that was the first times the derivative of the second. So we'll add the second, y cubed, times the derivative of the first, which is 6x squared. And that's equal to, on the right side, the derivative of y would be 1 times y prime plus the derivative of 1 is 0. So that's what we get for that whole thing. All right, so now, since we are looking at these, it says dy dx, and we're looking at this, I used y primes. Those are the same. I don't care which one you use for these. That was just to remind you of this different notation. Okay, so now what we want to do is keep all the stuff on the left that has a y prime and get rid of all the stuff that doesn't. All right, so here we've got x times 2 times y, so that's 2xy times y prime. And then the y squared times 1, that's y squared. That doesn't have a y prime, so we're not going to keep it over here. We will keep 2x cubed times 3y squared, so that's 6x cubed y squared times y prime. And then the y cubed times 6x squared does not have a y prime in it, so that's not going to stay over here. And then the other y prime from the other side, we need to subtract it, right? So what we did was we kept all the terms that had a y prime. So that came from here, here. Oops, not that one. But this one did have a y prime. And then what we want to do is move all the things that did not have a y prime over to the other side. So we'll get a minus y squared minus 6x squared x squared y cubed. All right, now once we've got all the terms on the left having a y prime in them, what we're going to do is factor that y prime out. So that first term we're left with a 2xy. The second term we have a 6x cubed y squared. And then minus y prime just becomes minus 1. And the right side we're not going to change. Okay, then once we've got that y prime factored out, we're going to divide by the stuff in these parentheses. And that's going to isolate y prime, so we'll have solved for it. So the right side stays the same. And then we'll divide by that stuff in the parentheses. Okay. All right, this time we want to find y prime for this equation, but at the point 2, 1. So what that means is we're going to find y prime and then plug in x equals 2 and y equals 1. So we're going to do just like we did before. Let's take the derivative implicitly with respect to x. So y cubed becomes 3y squared times y prime. For x squared times y to the fifth, we have to do the product rule. So the first will be x squared. The second is y to the fifth. So first times the derivative of the second is 5y to the 4 y prime. That's the derivative of the second. Plus the second times the derivative of the fifth. Whoops, not the fifth. The derivative of the first, rather. It's y to the fifth times 2x. And then we'll subtract the derivative of x to the fourth is 4x cubed. And the derivative of negative 11 is 0. All right, so again, just like before, we say, okay, this guy's got a y prime, this guy's got a y prime, and that's it. So we'll keep those, move everything else over. So that gives us 3y squared times y prime plus 5x squared y to the fourth times y prime equals. So we'll add the 4x cubed over and subtract 2x y to the fifth over. And now we can factor out a y prime and get 3y squared plus 5x squared y to the fourth is this same side on the right, 4x cubed minus 2x y to the fifth. And then isolating y prime, we're going to divide by the stuff in the parentheses. All right, so that's divided by 3y squared plus 5x squared y to the fourth. All right, so now if we want to, at the point 2, 1, we're going to plug in x equals 2. So what's 2 cubed? That's 8. 4 times 8 is 32. Minus 2 times x equals 2. So that's 4 times 1 to the fifth is just 4. So 32 over 4. And again, y is 1, so 3y squared is just 3. And 5x squared would be 5 times 4 is 20. Times y to the fourth is just 1. So it looks like we get 28 over 23. And that's our answer. All right, we plugged a point into the derivative. So the answer should be a number, not something with x's and y's. But our last example, so let's say that the price P of Sully's cookies is related to the demand X, right? So that's the number of cookies that Sully will sell, by this equation, 4x plus xp minus 9p equals 36. And so you should recognize this as an implicit equation. Here the input is the price and the output is the number of things sold. It says if the cookies are currently selling for $6 each, so that means right now $6 each, so right now P is 6. And the number of sales is 12 per day, so right now that's the demand. X equals 12 per day right now. So let's find the approximate change in sales if the price is raised by $1. Okay, so approximating change if the price is raised by $1, that should remind you of marginal change. And for that, we want to take the derivative and plug in these values. So what derivative are we talking about? So the change in sales, that would be the change in x. As the price changes means the change in x with respect to p. So we're looking for the derivative dx dp. And then what we want to do is plug in these values, x equals 6 and, p equals 6. Not x equals 6. So p equals 6. And x is 12. All right, so if we can find that derivative and plug those in, that's the answer we're looking for. Okay, so how can we do that? Well, what we'll have to do is look at this equation, 4x plus xp minus 9p equals 36. And in order to force something like a dx dp to show up, we need to take the derivative implicitly with respect to p. Right, so this thing tells you to take the derivative implicitly with respect to p. So 4x, taking the derivative with respect to p, you get 4 is the derivative, and then it was the derivative of an x. So we're going to multiply by, before we did multiply by y prime here, by the derivative dx dp. All right, then we've got an x times p. So this is going to have to be a product rule. So the first is x. The second is p. Take the derivative with respect to p, you get a 1. So that's the first times the derivative of the second, plus the second is p times the derivative of x with respect to p is just dx dp. All right, then we subtract the derivative of 9p with respect to p is just 9, and that's going to be equal to 0. Right, so just like before, we ended up with something that has the x's and p's, whereas before it was x's and y's, and dx dp's, whereas before it was y primes were popping up. Right, so since we're trying to find dx dp, we're going to keep the stuff that has a dx dp on this side. So that's 4 dx dp plus p times dx dp equals, and then the negative 9 when you move it over is positive 9, and the plus x when you move it over is minus x. And then we can see we're going to factor out a 4 plus p, and we'll divide by that to get dx dp is 9 minus x over 4 plus p. Okay, so then plugging in x equals 12 and p equals 6, we get minus 3 over 10. Right, minus 3 over 10. So the sales x will decrease by approximately minus 3 over 10 will be 0.3. So decrease by about 0.3. So less than 1 if the price. Okay, and we had one more example here. It says for Penny's landscaping first off, this is the example of related rates, which was on the first slide. And we'll see what that is. All right, so for Penny's Landscaping Company, the total revenue and total costs for the maintenance of X homes is given by this R of X and C of X functions. So suppose that Penny's adding 10 homes per day when the 400th customer is signed. Then find the rate at which the revenue, cost, and profit are changing per day. Okay, so here we have something per day showing up. All right, so per day should make you think that's a change over time. So if we're changing the number of homes X over time, that's something like dx dt, the change in the number of homes X over time. And that's the derivative of X with respect to t. And it says, since Penny is adding 10 homes per day, well, that would be changing at 10 homes per day. So that's saying this is 10 when the 400th customer is signed. So that says when X is 400. All right, so we know dx dt is 10. Okay, so that's what that sentence said. And why do we care about that? Well, that's going to show up. Where is it going to show up? Well, let's now try to figure out, the last sentence here says the rate at which, we'll just start with the revenue is changing per day. So the revenue changing per day, that is something like dr dt, change in revenue over time. Per day, which should tell you time. Well, what is that? That means we're going to go to this revenue equation and take the derivative with respect to t. On the left side, you get the derivative of the revenue with respect to time. That's exactly dr dt. On the right side, we're now taking the derivative of 1000x with respect to t, so you get 1000 times dx dt. And hey, that's the thing that we already know, so that's good. Minus 2x times dx dt. All right, so if we want the rate at which that's changing when the 400th customer is signed, what we want to do is plug in x equals 400. And when we plug in x equals 400, we get 1000 times, well, dx dt when x is 400 is 10. Minus 2 times x is 400 times dx dt when x is 400 is again 10. So this is 10,000 minus, 8,000? So that's 2,000. So that's the change in revenue per day. The rate at which the revenue is changing per day when that 400th customer is signed. For the cost, we'll do that one on the right side of this guy. So dxdt is still 10. That hasn't changed. But now, to get the rate at which the cost is changing per day, that'd be something like dc dt. And to do that, we're going to take the derivative of this cost function implicitly with respect to t. So the left side, the derivative of c with respect to t is just dc dt. 3,000, you take the derivative, it goes away. 20x, you take the derivative, and you get 20 times dx dt. So then plugging in 400 for x, well, that would be 20 times dx dt is 10 when x is 400. So that's 200. All right, so there's our answer there. And now for the profit, you could do this one of two ways. You could form the profit function as the revenue function minus the cost function and do exactly what we did. Or if profit is revenue minus cost, then dp dt end of 2.5.